Okay, good morning. Thank you very much. Welcome to the Seminar of Mathematical Psychology and its Application in its second season. Thank you very much for being here and for all your support. And as always, to my students, I am very proud of you, and without you, this would not be possible. Today, we have the great honor to have the participation of Dr. Marieke van Vugt from Groningen University. I had the opportunity to listen to Marieke during the annual meeting of the Society for Mathematical Psychology. It was the workshop dedicated to awry cognitive architecture. And I remember that after her extraordinary talk, I wrote to my student who was also present in the workshop, and I said to her, we have to invite Marieke. Marieke is an outstanding person and an exceptional researcher who I highly admire. And without further ado, allow me to introduce our guest with a brief review of her career. Marieke van Vugt is an assistant professor at the Institute of Artificial Intelligence and Cognitive Engineering, ALICE, of the University of Groningen in Netherlands. She obtained her PhD in neuroscience, focusing on the role of brain oscillations in recognition memory with Dr. Michael Kahane at the University of Pennsylvania in 2008. She then went to do a postdoctoral research on neural correlates of decision-making with Jonathan Cohen at Princeton University before starting her own group as a tenure-track assistant professor in Groningen in 2010. The research in Dr. van Vugt lab focuses on how, when, and why we might wonder, and what the fundamental cognitive operations are that underlie meditation and mindfulness. She investigates these questions using a combination of computational modeling, neuroscience, and experimental psychology tools. So, Marieke, thank you very much for this opportunity. Welcome to this seminar. The stage is all yours. Thank you very much for this.
Thank you very much for inviting me, and I'm kind of sad that I don't get to see all of you, but I hope one day we will meet in person. So for now, I guess we'll just have to do with the online version, but otherwise maybe we wouldn't have met at all. So yeah, today I'll share a little bit of the work I'm doing on MindWandering, and really asking the question of when is mind-wandering of benefit and maybe when is it not, and providing somewhat of a computational modeling perspective, but also sort of flavored with a pinch of psychology and neuroscience as well. So let's get started. And as always, I would like to get started by introducing some of the people who have contributed significantly to this work. So, of course, my colleague and boss, Professor Niels Tatgen, and then several of my students, Maarten van der Velde, Christina Yin, Marlijn Besten, and Stefan Hauser. So they're the awesome people who did this work. And so let's get straight into it. What is mind-wandering? So mind-wandering is typically defined in the scientific literature as a process of task-unrelated thinking. So this means that, like the person here in the example that's trying to write their paper, then suddenly their thoughts go to, I don't know, what they're going to have for dinner, maybe, in my case, maybe in your case, what you're going to have for lunch. So this is probably a fairly unharmful kind of mind-wandering. It probably doesn't really have as much of an effect on writing the paper, although if you have too much of it, then you never get the paper written. So then it starts to become somewhat harmful. But also it can be beneficial, and we'll talk about both of these cases in this presentation. And I'm very interested in when is mind-wandering beneficial or harmful, but also when does it occur? Can we sort of predict that using somebody's EEG and using computational modeling? So I would like to argue, to better understand what's going on with mind-wandering, we need computational modeling and we need neuroscience. So before we get into the computational modeling and neuroscience, let's actually define in a little bit more precision what we mean by mind-wandering, because mind-wandering has only been studied in the lab for the past maybe 10 years or so, or maybe, 15 years. And the reason is that at that time, people started to develop this, you could call it technology, to measure it, and which is done in a very simple way. You give somebody a boring task, And then every so often, you ask them the question, what were you thinking about just now? So you interrupt the task. And then the nice thing of that is that you can then start to relate objective performance in the task, such as accuracies and response times, to these thoughts. So you can ask them, were you thinking about the task or something else? But also, was it something positive or negative? Was it self-related or other-related? And those kind of things. And you can see whether, say, they make more errors if they report thinking about other things than the task, which obviously you would predict. So one task that's often used, that's a perfect example of a very boring task, is the sustained attention to response task. Basically, what you have to do in this task is every few seconds, there's a stimulus that comes on, and most of the time you have to press that stimulus. It's a so-called go, no-go task. So in this case, this is, you have to press whenever you see an O on the screen, but every 1 in 10 or so stimuli is a cue, and you should withhold your response to the cue. So you can imagine that if you have somebody do this for an hour, a typical duration of such a task, this gets pretty boring. And so there's plenty of time to mind wander. So if you ask them about once a minute or so, what were you thinking about, then you would tend to find that roughly half of the time people report mind wandering. So let's actually try this out ourselves. Let's see whether this is going to work. So, you know, if you're a person doing this kind of an experiment, this is kind of what it would look like for you. So you see an O and you press a button, O, press a button, press a button, press a button, press a button, not press a button, press a button. Well, you get the point. Are you already mind wandering? Okay, and then I will ask you, what were you thinking about? And you might say, I was thinking about the task. I was perfectly focused. Or you might say, well, you know, I was kind of thinking about how I was doing on the task. Or you might say, well, I was distracted by the environment, some noises that I hear. Or I was daydreaming. I was like, you know, screw this. I'm going to think about I don't know, ice cream or something. Or maybe I just totally was blank. I didn't think anything in specific, maybe especially when it's early morning, that might happen. So that's literally what this feels like. So when you have people do this kind of a task, typically what you find is, at the moment they report that they are on task, they are a bit more accurate than when they're mind wandering. So here we're plotting the difference in accuracy between mind wandering and on task. And so in the SART task that I just showed you, but also in a visual search task, you see there's a reliable decrease in accuracy for people when they're mind wandering compared to on task. And also you tend to see changes in response time. So for people in the SART task, they tend to be a bit faster, but during a visual search task, people tend to be a bit slower. So the response time effects are a bit more variable. They depend quite a bit on the task, which makes sense because, for example, for this SART task, what happens when people start to get distracted, they just go into a rhythm of just pressing a button almost before they've even seen the item, the stimulus on the screen. Whereas with a visual search task, there's not such a strong rhythm in there. And instead, what will happen is that they will just kind of miss the picture they have been given, and they might think for a long time about, well, you know, what was on the screen. So yeah, these are basic behavioral effects of mind wandering. So yeah, here you would sort of seem to think that mind wandering is not so good because you do poorer on your task. You typically get more variable and slower response time. I actually don't show you the data for more variable, but that's another thing that's been found. So it's not so great. But sometimes, actually, mind wandering can also be good. So this is an important thing I want to mention in this task, in this talk. Mind-wandering can, for example, also lead people to have more creative solutions. So if you think of it, starting to mind wander in a boring task like the mind-numbingly deadly task that we give people in the lab is actually pretty healthy. Like, people are not robots, and it's kind of good that they start to think of other stuff when they're in this kind of a situation. And lo and behold, Ben Baird and colleagues found that when they gave people an undemanding task, actually in the task that followed, they did better in generating creative solutions than when they were doing a demanding task, or even when they were not doing any task at all. So creativity is one way in which mind wandering can be beneficial. And another situation is, for example, planning. So rather than focusing all your attention on such a stupid task, which is really not that useful, you're only doing it because the researcher wants you to, or even in real life, sometimes you're doing fairly stupid tasks, and that's fine. But then it's also good that you are starting to plan other things that you're also doing. So when you're doing this boring task, you might already plan out how you're going to walk through the supermarket to get your groceries afterwards, or how you're going to cycle home. I guess that was in a time when we would go to work. I don't know what it's like in Mexico right now, but here we're still mostly working from home. So I guess then you're not cycling to work. But anyway, sometimes I'm still cycling to work here when I'm lucky. So yeah, anyway, planning is something that we still have to probably do, even if it's like, how am I going to cook this meal? So yeah, those things are pretty adaptive. So before we're going to go a bit more into data, let's try to think a bit more about why modeling is useful. So the question really is, we observe these effects, right, of mind wandering. So sometimes they're not so useful, like you see performance decrements. Sometimes it's useful. So can we explain why mind wandering leads to performance decrements, or in what circumstances it's actually useful? So to do so, the solution we use in my lab is to make a computer model of the task. So basically, we try to simulate what a human is doing, and then we compare the human and the computer to validate whether our model is actually making sense. So I have a little movie. I'm not sure whether this is going to work, but let's try.
Our brains can support a wide variety of activities, from cycling to studying French. How is that possible? That's what we're trying to find out. Not only to be able to build intelligent robots and computers who think just like we do, but also to understand brain diseases better, so we can help those suffering from brain disorders. Many scientists try to understand how brains work by studying how they react in different situations. We try to simulate the human brain. We build a computer model of how we think the brain works, and then we compare its performance to the performance of real brains. This way, we hope to understand how different brain parts work together. Your brain, for example, has a working memory, a kind of sketchpad for maintaining information temporarily. There is a visual part of the brain where the images from your eyes arrive, and a place where sounds coming from your ears are processed. There is also a long-term memory, which remembers where you live and who you are, a part that moves your muscles, and there are several other parts, some of which we don't even know yet. But how do all these bits work together? What pieces are there? How do they work? How are they connected? We think you can figure that out by trying to build a copy. We program a computer to have a working memory just like in our own brains, and a long-term memory that forgets things at just the same rate as real human memory. And in the computer, we can connect all that. This is how we get simulated brains. You can test these fake brains. But first, we test the brains of actual people. For example, by having somebody drive a car and talk at the same time. This is possible, even though you do two things at once. But when somebody tries to text as well as drive, things are likely to go wrong. Why? Let's see what our computer brain does. In this model, the eyes are connected to the visual part of the brain, which is connected to working memory, just like the hearing part of the brain. It is possible to talk and look at the road at the same time. But if you're texting while driving, the visual brain has to route two streams of visual information to working memory, and that is impossible. If the computer model's performance matches real people's performance, then our model might be similar to how our brains really are. Often, our computer models can already predict which brain regions become more active. This way, we try to find out how the brain works. Try to build it like you think it is, and then check if that squares with our knowledge of the real brain. And if it doesn't, it's back to the drawing board.
So basically, this is what we're using. This is the kind of logic we're using. So we're trying to build the mechanism that we think underlies mind wandering. So what is mind wandering, really? Well, we conceptualized it as follows. Basically, the idea here is that when you're mind wandering, you have sort of a process that's competing with the main task you're doing. So here on the left side, you see your main task. You have a task stimulus, you're bringing your attention to the task stimulus. And to keep it on there, you have to actively engage with the task stimulus and sort of metacognitively monitor whether you're still attending. Because the moment your attention grows weak, it can be captured by something else, some competing process. That we call the thought pump. This is a very nice concept that I got from David Meyer from the University of Michigan. This thought pump likes to just pump thoughts into our I guess, consciousness in a way. And one memory tends to retrieve the next memory and so on through a process of associative elaboration. So this is sort of how our mind sort of wanders in this memory landscape. And, this idea is really consistent with some neuroscience literature in which they found that just prior to a person reporting that they are mind wandering, you tend to see this activation in the medial temporal lobe, suggesting that indeed it is a memory process that first pops up, and then the dorsolateral prefrontal cortex either lets the memory through and you sort of elaborate on that, or the dorsolateral prefrontal cortex says, no, we should be paying attention and stick to the task. Then say, we are mind wandering. So the dorsolateral prefrontal cortex has not led us through, and we are thinking about the task. Then how do you get back to the task? Well, that works in my model as follows. Sometimes you hit upon this memory that says, I am supposed to be attending. And that reminds you of the task, and then you can go back straight to focusing on the task stimulus. So this is, pretty simple kind of process, but you can translate that into computer code, like I mentioned in the video. So basically, the mind-wandering model is based on two principles. Mind-wandering is predominantly a memory recall process, and mind-wandering is a process that's in direct competition with the task. So the balance between the paying attention and the mind-wandering or the thought pump process sort of determines how often and how much you're mind-wandering compared to paying attention to the task. So the way I then modeled this is using a so-called ACT-R cognitive architecture. ACT-R means adaptive control of thought rational, and it was developed by John Anderson from CMU. And basically, this is like a programming language of cognition. So you have different kind of cognitive resources that you can then write algorithms with. So you, for example, have a memory process that was also mentioned in the video. There are visual resources that have to do with perception. Imaginal is like a working memory, like this sketch pad in your mind, and motor is like what you need to press a button. And for all of these, they have particular properties. So, for example, it takes a certain amount of time to engage. In case of memory, it might fade with a certain time constant, that kind of stuff. So you can use these cognitive resources to then turn the story that I just told you into an algorithm like this. So it consists of these terrible Lisp statements. That's how ACT-R works. It's written in Lisp, although there's nowadays also Python wrappers that allow you to interact with Ectar in Python. So for example, there is a so-called production, which is basically an if-then rule that might be starting the MindWandering process. And it says, well, you know, if in my retrieval buffer, there is a goal that says get distracted, then I'm going to transfer this goal to my goal buffer, and then I'm going to use my retrieval buffer to actually get something from my memory, and I'm going to empty my working memory because I'm busy thinking memories. So that's just one of those, and you write many of these rules that just basically implement the story I just told you. And then you use that to interact with a task, basically exactly the same task that we give to our participants, and we predict responses and response times. And then we see whether the behavior on such a task matches up with what the model does. So we give it exactly this task that I just mentioned. So every few seconds, we present an O or a Q. Only 10% of the time it's a Q, and 90% of the time it's an O. And according to our model, the way this works very simply is when you see a stimulus, the model first perceives it, processes it, determines what kind of letter it is, and then retrieves the stimulus response mapping for that letter. And if it's an O, then the response mapping is press button. And if it's a Q, then the stimulus response mapping says do nothing and wait and keep checking whether you're attending. Now, at some point, your thought pump is going to kick in and you start to, set your goal to retrieve memories. Now, of course, at this time, your memory is very busy retrieving memories, so you cannot at the same time retrieve the stimulus response mapping, kind of like in the video where we had the competition between driving and seeing stuff on the road and reading an SMS. So then you would predict that you see the cue, but you do not retrieve the stimulus response mapping, and then you just follow the default response of pressing a button. So that's the very, very simple model. And then basically you can test whether this model can predict basic behavior. So in this case, we can see what its accuracy is. And here in gray, you see the empirical data from the study by Bastian and Secours. And in white, you can see the model, and you can see it's not too bad. It's not perfect either, but models are never perfect. Response time, also pretty okay, at least within the confidence ranges. The coefficient of variation, so variability of response time, the model is a bit more variable, but still in the ballpark. Most importantly, the computer can actually introspect. So if we look at how often is the model distracted, you can see that empirically, people are on task about 60% of the time. So they're mind wandering about 40% of the time. So if we have 30 people listening to this talk, then I guess about 10 of those are 10 to 11 might be thinking about something else right now. Always fun to come up with a real life example. And in our simulation, we almost get exactly the same number. So yay, this model can introspect. And we can even ask the computer, what were you thinking about? Were you thinking about the future and the past and the present? The way you do this is very simple. Whenever the model is retrieving a memory, we also give the memory certain kinds of properties. So is it about the self or the other? Is it about the future, past, or present? Is it positive or negative? I mean, you can go anywhere. I will talk more about this when we get to the depression model, but this is the basic idea. So now we have an introspecting computer. Where should we go from here? Well, actually, before we go into when is mind wandering of benefit, let's see when is it not of benefit. And one persistent problem, I guess, especially in this time of COVID-19, the pandemic is depression and rumination. So rumination is this process of narrowly focused, uncontrolled, repetitive thinking, mostly self-referential and negative. And, it's these worries about what's gonna become of my life. Maybe even, I can't cope. I don't know how to survive. Nobody likes me, that kind of stuff. And it's Obviously, in periods of stress, that is particularly pernicious. And it's a core mechanism of depression. So that's why I think it's really important to understand it. And in terms of mind wandering, it has a fairly straightforward connection because, like Helena Christoph would say, it's a very constrained form of mind wandering. So rather than just wondering about all the possible memories that you have in your mind, you would sort of go around the same circle again and again, like, I'm worthless, nobody likes me, this life is meaningless, I'm worthless, this life is meaningless, nobody likes me, and just you can't get into any other perspective. Okay, so that's the story phenomenology. Can we turn this back into an algorithm? So one aspect of that is probably that you would have more negative memories available. How can we make that into the ACT-R model? Well, we can just increase the number of memory chunks that the model is sort of walking over that has a negative valence. What this does, though, that you might say, well, that's kind of trivial, but how would that impact the task? Well, one important thing is that the task is probably not negatively valenced, at least we hope not for most participants. So that means that the memory of the task, the more there's a competition from these negative memories, the more difficult it is to get back from these negative memories to the neutral task memory. And this is particularly compounded when we connect these negative memories very strongly to each other. So in ACT-R speak, this is like spreading activation of memory between memories that have the same valence. So if we set this to be stronger of the same valence, then it's more difficult to switch from negative to, say, positive or neutral. So we do those two things, and then we can look at what our model looks like. Now, there's one thing. You might wonder, how did we get at these numbers? How many negative chunks do we put in there? Like, is it 10 or 50 or 100? And, how do we get these numbers, 0.1 or 0.01? Well, what Maarten did, Maarten van der Velde, the at that time master student who did the model, is he looked at data from so-called experience sampling. It's a very interesting technique in which you ping people 10 times a day or so and ask them what they're thinking about. So nowadays, with the smartphones that are ubiquitous, this is fairly easy to do, and you can collect really cool data. And they give an impression of what people think about in real life. So not just in the lab, but really what do they think about in the real world. And in this case, we're looking at a data set from 2015 in which they asked 129 depressed participants and 212 controls about their thoughts 10 times a day for 5 to 6 days. And what they found, here on the left, we have the actual data. On the right, we have the sort of model equivalent. So here is just a plot for how often they give a particular rating. So if you ask them how positive were your thoughts, so they score 1 is not so positive and 7 is very positive, then you can see that the depressed people, they are in blue, they tend to rate their thoughts to be fairly low on the positivity scale. Their positive affect is fairly low. This is actually using the PANAS, the positive and negative affect scale. So this is the positive affect part. Now, healthy people rate it much, much higher, and they're in orange. And our model is sort of showing a similar dynamic. It's not exactly the same. So you can see these axes are different because we don't have a mechanism in our model to give responses in these sort of discrete categories. So we just look at the average activation of positive and negative memory. So it's not exactly the same, but it's sort of the closest we could get. I can talk about the technicalities later, but that's the idea. But still, we see the shift. So healthy people in orange are more positive than depressed people. And conversely, if we look at negative affect, then the average score of the depressed people in blue is higher than the healthy people in orange. And we see the same with our model. Okay, so that's cool. And we looked at more things with our model, but just for time's sake, I'm just going to go straight into then. Once we've put these parameters of the model, like how many negative memories and how strongly are they connected, if we put them, we fix them on the basis of this experience sampling data, what kind of predictions does that make for performance? So why don't we give the model again the same task that we give that we would give to real life participants? So there's again this SART task in which people see O's and Q's and press buttons whenever they see an O, but not a Q. And we look at their response time and accuracy and variability. And how would a depressed model behave in such a task situation? Well, we know that people who are suffering from depression overall tend to do not so well on cognitive tasks. So very often they are just distracted by all these ruminating thoughts, which just pull them away from the task. That's indeed what we found in the model simulation. So here we are looking at accuracy. On the no-go trials, the difficult trials, we see that controls are about 70% correct, modeled depressed individuals. These are just pure model predictions, not changing any parameters. You can see that they do worse, and there is no difference really in the fraction on task and variability of response time. Although the patterns do go a little bit in the right direction, where you would see a bit of impairment, but it's not significant. Okay, so then that's just a model prediction. So is there any sense that this is borne out by real life data? Well, the short answer is we don't know, but these are some preliminary data that we have collected in the meantime that we're gonna publish at some point. Still working on the paper. It's looking at not really full depressed patients because it's more difficult to get those, but say we just take university students and we ask like, what is your tendency to ruminate? What is your depression level? And just on the basis of questionnaires, we have people that are more ruminative and people that are less ruminative. And then we can compare their accuracy on this no-go trials, and you can see that the students, they are doing better on this task when they are not so depressed compared in yellow compared to when they are more depressed in blue. And this in this case, we're also doing some interventions with them. So we did one block of the task after a positive challenging intervention, that's a therapy technique, and the other after a public speaking intervention, which is a stress task really made to induce ruminative thinking. And you can see that especially those people who already have a tendency to rumination, when you give them this terrible trier social stress task, then they start to do worse on the task. So yay. The empirical predictions are somewhat in line with our model. So there is something to our model. So and at the same time, it helps us to think more precisely about what are the mechanisms underlying depressive thinking, or at least one aspect of depressive thinking. And the nice thing is that because we're using models, we can also go beyond the task that we measured. So then we used the same kind of mechanism to predict working memory performance. So this is a case in which people were making decisions about happy and angry faces, and their data from Levens and Gottlieb, published in 2010. And I'm not going to go into the complexities of the task because it's fairly complicated, much too complicated to talk about in this brief talk. But basically, all I want you to focus on is, and you can read this paper if you want to know more. It's an ICCM paper from 2018. But basically, what I want you to focus on is the overlap between the darker colors, which are the data. So in the blue, they're control, and the brownish, it's depressed. And then the lighter colors, they are the model. So bluish is model, and yellow brownish is also model for the depressed individuals. And you can see that the fairly complicated pattern of response times across happy, neutral, and sad faces is replicated by our model. So by applying these principles that, people with depression, they tend to get stuck on retrieving negative information and thinking about that for longer times, we can predict not only performance deficits in a boring sustained attention to response task, but also in this complex working memory task and back task, in fact. But we also had to add a model mechanism, namely an attentional bias to negative information. So there's a little bit more to it as well. So that's probably also a crucial mechanism underlying depression, which was only uncovered when we went to this more complex task. And then we're also now working on free recall, where we're looking at what are differences between controls and depressed individuals in terms of their the kind of performance they engage in. So this is even more preliminary data, where basically in this ACT-R model, where again the model keeps going, keeps sort of persisting on negative information. If you then give it a list to learn of positive, negative, and neutral words, then the depressed model tends to start its recall less often with a positive word. Like here you can see, what does the model start with positive in green on the left, and does it start with a negative word in pink on the right. And you can see that the depressed model prefers to start with a negative word, and the healthy model prefers to start with a positive word. So I'm also trying to fit this to some empirical data, but again, work in progress. So just to give you an idea of what we're doing here. And then finally, what causes this ruminative mind wandering? Well, one thing is probably that it's about the self, and this self is a particularly sticky thing to think about. So it tends to capture you and makes you very difficult to disengage. So for example, one way that we know this is we ask people to engage in a complex working memory task in which they alternated memorizing stimuli with either, in one condition, thinking about whether words refer to yourself, so this is the self condition, whereas in the control condition, they made size judgments about objects. And then we asked, does thinking about yourself increase the tendency to mind wander? And yes, that's what we found. So in some paper, some work by Stefan Heiser, we found that in the self-referential condition in orange, we see that people are on task less than in the control condition, but they are more often elaborating on these words, which is really on themselves. And any of the other categories of mind wandering did not really change. And that also impaired task performance. So here we have blue, the control, and red is the self-referential. And you can see that the number of words that they can correctly maintain is lower for the self-referential condition than for the control condition in blue. So self-referential is red and control is blue. And this was true for, we really replicated this, I don't know, 3 times. It's probably the results of my lab that I have most confidence in whatsoever. And we were able to also predict this with an ACT-R model that basically assumed that this self-thinking was just more sticky. We just persisted on it for longer. And yeah. Also, in a different kind of task, when we went back to a very simple SART task, we also found that a certain kind of thoughts tend to be sometimes more difficult to disengage from, and those are probably mostly the self-related thoughts. So when people say, you know, the thought I was thinking is a bit difficult to disengage from, then they tended to do worse on the task. So here is no-go accuracy. And when people say, I'm just thinking a neutral thought, their performance is intermediate. But when they say the thought is kind of sticky, I find it hard to let go, then you can see they do much worse. And when they say, well, it was quite easy to just let go of that thought, then people do much better. And it's interesting that people are so aware of that. And also you can even find differences in their pupil size, depending on whether the thoughts are easy to disengage from or difficult to disengage from, or sticky or less sticky. And yeah, so we can even see this in pupil size, and we're now looking at EEG data where we find similar things. So it seems like when you're engaged in this self-related process, self-related thinking, often negative, that's also difficult to disengage from, then not only does it harm performance on task, but we can even see that you're processing incoming information less. So we can detect that in pupil size, we can detect that in EEG. Okay, so this is all where mind wandering is bad. But I was, you know, the title of my talk was really about when mind wandering is good. So let's move on to that. So when is it useful? As I indicated before, probably one of the most useful functions of mind wandering is planning. It's like you're doing this boring task, filling out a bunch of forms, and meanwhile you're thinking about, you're planning going out for dinner, or maybe planning making your dinner at home, when nowadays you can't really go to restaurants very much, depending on where you are. So planning. So yeah, we have some evidence for that, you know, very often when thoughts are, there are many times that when people are reporting thinking not about tasks, that those are about the future, and that those are positive. So also thinking about the future and positive tends to go together. That's what these data by Ruby and colleagues show. So do those reflect planning? Now, a challenge with that is, how do we bring planning in the lab? Because yeah, we can't really tell people, now go plan your dinner. It's not something that you can control. So how do you do that? Well, what we decided to do was to come up with a two-stage task in which it would be natural to go plan, but people wouldn't be forced to plan. And then we could see, like, how often do people naturally engage in that, and does it help them? So what we did was we gave people this screen, and we did a boring and back task on the left side of the screen, which people did first. But then on the right side of the screen, there was this other task that people knew they had to do after that. And the task on the right side of the screen is kind of a complex task in which you have to use 3 operations that you have to apply to the 2 words that you see here. So the top instruction says, well, negate the second word. And then you have to decide whether the second word is loud. And so you have to answer the question, is this loud, the horn? And then you have to negate that answer. So loud would be yes, but then you have to negate that, it's no. And then you have to use your left index finger to press that button if it's the yes response, and some other finger if it's no response. You can already imagine it's quite complex. But the nice thing of this kind of a task is, it's called a RITL task, rapid instructed task learning task, is that you continuously sort of update the kind of instruction, and people would probably do better if they already get this instruction going in their working memory, if they sort of prepare a task set for that. So our question was really, do people, when they're doing this task, already sometimes move their eyes to this task as if they're planning to do that? And so we track people's eyes while they do this task. And lo and behold, people do that. So we then looked at, do people that move their eyes to the other task, do they do better on this other task, the complex task, the riddle task on the right side of the screen? If we look at their error rates, not as much different. So these are funky violin plots. You can see here the white is they didn't prepare, so they didn't move their eyes to the right side of the screen. And blue is they did prepare, so they did move their eyes to the right side of the screen. You can see that really there's no difference in error rate. So these are actually 3 versions of the task on the left side. So you can imagine that when whether you're going to plan depends for one on what kind of person you are, whether you're always planning. Like if you're like me, then whenever you're somewhere, then you tend to think about all the other stuff that's still going to happen, get quite excited about the future. But maybe other people are less like that. But whether I tend to plan out my future also depends on whether I'm doing something that is cognitively demanding. Like when I'm giving a talk, I'm probably not thinking much about the future because I need all my brain power to give the talk. But when I'm filling out some forms, I might be. So we try to manipulate that by giving a very simple task, then giving them a choice response time. I think that this was just basically pressing buttons or something, and then a choice response time task in which, when you saw one stimulus, you had to press one button, and the other stimulus, you had to press another button, and then an end back task, which is even more complicated. So we found that basically there was still, depending on the task, not really much of a difference in error rate between the 2 versions, or between the planning and no planning versions of the task. But we did see a benefit in response time, especially when they were doing a very easy task on the left side of the screen. So obviously, when you're doing an easy task, it's quite possible to go plan something else. But when you're doing a complex task, planning, you don't really have time for that. So you don't see that much of a benefit. So actually, while the slide says submitted, I would say that it's actually now already in press at JEP General, I think. So only with low task difficulty, we can see that people engage in planning, which is kind of consistent with the kind of observations that we have probably from our own lives. So this is a way in which we try to really empirically grasp sort of planning in the lab. We haven't made a model yet to describe these data, but yeah. Obviously, we first needed to get the data, the behavioral data, and you can see it's quite intricate. So then the last bit of my talk is tracking mind wandering in the brain. So not only do we want to, assess what are the effects of mind wandering on performance, but ideally we'd also want to predict when somebody is mind wandering based on some objective kind of data. So in my lab, we do a lot of EEG. And the nice thing of that is that if we can track mind wandering without asking people on the basis of objective data, that would be really nice. So we're using EEG for that. So we record people's brains while they're doing our funky search task, like in A, or visual search task, like in B. And so in the start task, again, in this version, you see words and you press a button whenever you see a word, except when it's an uppercase word. And then every so often we have these thought probes. So we ask people, were you paying attention to the task? If they say yes, then all the trials, like 5 trials before that, get labeled as on task. If they say I was thinking about something else, then the 5 trials before that get labeled as mind wandering. And you could do the same with the visual search task. In this case, the visual search task is like, is there a blue circle in this? And then, yeah, people just respond to that. And again, they have a thought probe. Are you paying attention to the task or something else? And then you label the EEG based on their response. Then you give this to a machine learning classifier and you give it many examples and you say, this piece of EEG was mind wandering, this one was on task, and now figure out a mapping between the EEG activity and this label of mind wandering and on task. We found that support vector machines are the best ones, especially the nonlinear support vector machines with a radial basis function, and see how well the classifier does on the EEG data. So it makes predictions on single trials. Turns out this is a challenging problem. So here we can see prediction accuracy for all of our 17 individuals in the first study. And you can see that the classifier is above chance, but overall it's something like 60% correct for both the visual search and the SART task. The only cool thing that we found here is that when we trained a classifier on SART, then we could to some extent also transfer this to visual search and the other way around. So that's what the purple and the blue accuracies are. So we were able to develop a task general classifier, and now we're working on a deep learning classifier on this. We find that actually it doesn't get much better with deep learning, but we're still able to do a fairly task general classification, even across experiment classification. But yeah, getting close to 100% is definitely not an option in our hands, at least. And if you wonder, like, what aspects of EEG does this mostly zero in on, and then you find that it tends to be alpha oscillations in the back of the brain. So A10 is a channel that's sort of on the back here, as well as C21. It's another channel that I think is somewhere on the back. And there's also the P3. That's another relevant EEG marker. Okay, so I'm not gonna go into this. I just wanna, in the last few minutes, talk a little bit about, well, can you generalize this to more real life situations? Because what I've so far talked about is a fairly abstractified situation of people doing a very boring task in the lab, which is what we mostly do. But what if we try to do something else completely outside the box? So I work with Tibetan monks in India, and these monks have very interesting practice of monastic debate. So we went to the monastery and we see them debate. I'm not going to go into that for now. But we also recorded their EEG while we're debating. And then you can see some other monks here in the background. Those monks are rating the debating monks about whether they're focused or distracted. And then we took those observer-rated pieces of EEG and trained classifiers. And we got some reasonable accuracies. Of course, I'm still taking this with a grain of salt because it is based on fairly small data sets. But you can see that overall, different classifiers like support vector machine, random forest is one of the best performing classifiers. You can see it does pretty well, and especially the ones in the lower frequencies like the delta and theta. And here's an overview of channels that are being used. So yellow is more being used and blue is less being used. So you can see it's kind of a whole brain, seems to be a whole brain sort of classification solution. Now, I do think that this has to be replicated because it's, again, based on a fairly small data set, but at least I think we can conclude that classification is possible, even in real life situations. So I think that's interesting. So that leads me to the conclusions of the whirlwind of stuff I've talked about so far. So one is that mind wandering is pervasive. We do it about half of the time. It can be harmful, but it can it can also help task performance, and mind wandering studies are useful to understand psychiatric problems like depression. But we can also use it to bring planning into the lab. And then you can also use machine learning to try to find out better how does mind wandering change over time. And that's basically all I wanted to share. And I'm happy to answer any questions.
Thank you very much, Marieke, for this very interesting talk. Thank you very much. We have a couple of questions from Andrea. Hi, Andrea from here. She's asking, when one is mind wandering, which are the main brain
So
areas that we
I
use?
guess I in the later part of my talk, I already indicated a little bit with EEG that we find that these posterior alpha oscillations are quite relevant there. This in general has been related in fMRI to the default mode network. So that's like posterior cingulate cortex, medial prefrontal cortex, and probably also medial temporal lobe is relevant for mind wandering.
Perfect. Another question from Andrea. Can we also model mind wandering on TDA? And if attention deficit can be taken as mind wandering?
I'm not sure what TDA means. Okay, so that means just ADHD. I guess. Yeah. So probably yes. I guess the big question you would need to answer is, what do you think is the predominant mechanism underlying ADHD? So is it, for example, that a person with ADHD has more memory? Is the distraction process stronger, or rather is the focus process weaker? Maybe do they have more distracting memories that are more active, or is it just that the dorsolateral prefrontal cortex lets everything through and doesn't really control the level of focus? But you could even compare different possible explanations. So I would say that in principle, it should definitely be possible to model that. But you need to spend a bit more time thinking about what would be the mechanism.
Thank you very much. Andrea is asking another question. Mind wandering is a decision, or is something that just
I would say probably both. Sometimes, so there are studies by Paul Seeley and colleagues that distinguish between intentional and unintentional mind wandering. So as one of these questions, these thought probe questions, you can also ask the person, were you mind wandering intentionally or not? And to sometimes people are mind wandering intentionally when, again, it's a boring task and they find this thinking about whatever they're planning, their future life, or whatever, they find that more interesting than thinking about the task. In that case, the mind wandering can be intentional, and sometimes it's unintentional. So yeah, we haven't really done any work in my lab so far on working on that, but I think it is still a very relevant and interesting distinction.
Perfect. I have a question of my own. I don't know if you have thinking about this in this situation that we are living, about mind wandering and online lectures that the students are having. I don't know if you have thought that.
Yeah. Obviously, at least I notice for myself that I tend to mind wander a decent amount during online lectures. Probably more than I'm not sure whether it's more than in real life or not. I guess I think it's probably more because it's still somehow not as real as seeing a real person in front of you. So I guess the inherently the task process is weaker compared to what you would have in real life. So that then it's already sort of behind in the competition with the thought pump. And maybe also nowadays in the pandemic time, the thought pump might be more active because we have quite a few worries and uncertainties that drive our mind wandering. And we, on the other hand, I would say that also during lectures, mind wandering is not necessarily negative, because apart from it being possible to the possibility that mind wandering reflects planning the future or worrying about things, it can also be a mental elaboration of the stuff the lecture is about. And I would argue that that's in fact quite critical to understanding the lecture. So that's another quite adaptive kind of mind wandering process. So yeah.
Okay, and we have a final question from Roberto. Says, I'm curious if mind wandering about oneself increases distraction. Do you think it will be a specific kind of meditation technique or thinking technique that will be more suitable for depressed people?
Yeah, so overall, I would say so far the evidence is that mindfulness-based cognitive therapy is quite good for people with depression. So not just having mindfulness in which people become more aware of their thoughts and realize that they're just thoughts and that it's possible to drop them, but also giving them some psychoeducation and behavioral training techniques in which they can really modify the content of their thoughts and become more aware of, oh, these are maladaptive patterns and actually they're not so real, I can change them. So, and that's, I would guess you could maybe consider them that reflecting, modifying how many thoughts, how many memories are how these thought patterns, how strong the thought patterns are about yourself or not. So, yeah.
Perfect. Thank you very much, Marieke. And I would like to ask you for a final message. As I told you at the beginning, most of my students are from undergraduate degree in psychology. So I would like to give you a message for them in order they maybe want to dedicate or do some research in this area. I would like to ask you for this final message.
Okay. Yeah. I would say just for all of you, just follow your curiosity. I mean, the fantastic thing about research is you just get to learn new things. And I think in whatever capacity you end up, whether it's research in academic career or elsewhere, learning is probably what keeps you healthy, what keeps you young, and what can keep your life rich. So just keep learning and follow your curiosity because it can really bring you in places that you never thought of. I mean, I'd never really considered how I'm studying all these cool things now that I never even knew about when I was younger. So just keep exploring, I would say.
Perfect. Thank you very much for that message, Marieke. And thank you very much for this great opportunity to hear your experience, your research. I hope you have a good time with us.
Thank you. Yeah, it was great to meet you all. And thank you for your questions. They're great. And yeah, lots of good luck with everything.
Yes, so I'm going to stay a little bit longer, a couple of minutes with Marieke after the end of broadcast, but I want to mention our next talk is going to be on October 20 with Rachel Wu from the Department of Psychology of the University of California, Riverside, Learning to Learn Across Lifespan. And also we had an outreach lecture from Dr. Alberto Guijosa about the string theory, gravity, and dimensions. So stay tuned for all the activities that we have. And thank you very much again, Marieke, for this great opportunity. And thank you to all that we were here in the connection. Thank you very much and see you next time. Be safe. Bye.
Bye.